Yes, sir.
Okay. Okay, so we were discussing about the various factors that causes the signals to degrade in optical fibers. So the major causes are, so you can have two classes. So one is called as attenuation, which causes the signal to lose its strength. So physically you lose the number of photons that will be transmitted. The other category or the other reason for signal degradation is a dispersion, which we will see later. So, so I hope all of you have downloaded this paper written by Charles Cow, Dielectric Fiber Surface Waveguides for Optical Frequencies. So if you are not downloaded, please download this and read this paper. It's very important. And it was in this paper that the author pointed out that the major causes for losses in optical fiber is because of the presence of impurities that are present in silica. So you can have certain foreign impurities that are present in silicon that can be responsible for what is called as the material absorption inside optical fibers. And the material absorption could be intrinsic losses, it could be an intrinsic absorption, it could also be extrinsic absorption. So intrinsic absorption is because of the presence of the intrinsic material. Intrinsic material means, as you know, optical fibers are made out of silica or silicon dioxide, which is silicon Si double bond O and another double bond with O. So you have two atoms of silicon, sorry, you have two atoms of oxygen and one atom of silicon. So these silica bonds or silicon oxygen bonds can, in fact, can absorb some of the light, and those losses or those absorption losses is what is called as the intrinsic material absorption loss. So intrinsic loss is because of the presence of the native material. So if you want to avoid intrinsic loss, then you will have to avoid silicon dioxide, and unfortunately, as of now, silica is the best material for making optical fibers, though there are other kind of materials. For example, you can also find polymer fibers. You can find optical fibers made out of polymers or something made out of plastic. So even though these materials can also be used to make optical fibers, nevertheless, the still preferred medium is always going to is still silica. So there is always a limit for which you can minimize the intrinsic material absorption. The other cause for the material absorption loss is due to the presence of extrinsic materials, and these extrinsic materials is what is called as impurities. So in fact, if you have these kind of metals present inside silica, you would see that the absorption loss is going to be very large. So for example, if you have copper, so Cu2 plus, so if you have copper ions present in silica optical fibers, for example, if you have 1 part in 10 raised to 9, that means out of 10 raised to 9 silica atoms, let's say that you are having 1 copper atom or you are having 1 copper ion. Then it turns out that at 850 nanometer, the loss is going to be 1.1 dB per kilometer. That means, so this, what it physically means is that if you have 1 copper ion out of 10 raised to 9 silicon atoms, so 1 copper, so 1 Cu2 plus out of 10 raised to 9 silica bonds or silica atoms, you are going to have a loss of 1.1 dB per kilometer. So this chart actually illustrates the importance of the presence of impurities. So this means that you'll have to minimize the presence of impurities as small as possible so that the losses can be minimized. So in fact, the presence of water vapor is also responsible for the losses is also responsible for the losses in optical fibers. So you will see, so if you experimentally measure the absorption losses inside an optical fiber, you can find two peaks. So one peak somewhere around 1.2 micrometer, somewhere around 1.2 micrometer. The other one somewhere around 1.4 micrometer. So these two peaks, they are called as the water absorption peaks. So again, all these losses are a function of wavelength. The loss is never a constant, it's always a function of wavelength. So if you measure, if you observe the experimentally measured absorption spectrum or the losses inside an optical fiber, you will see that you are having two minimas here. So one minima happens to be around 1300 nanometer or 1310 nanometer. The other one happens to be around 1550 nanometer. So in fact, among these two, the loss at 1550 nanometer is going to be the least. And therefore 1550 nanometer is the most preferred wavelength for optical communication. The reason is because the losses are going to be the least. Now 1300 nanometer or 1310 nanometer, so this window is also preferable for optical communication. However, it's preferred for some other reason. The reason is because at this wavelength, so we'll see that later, at this wavelength, the dispersion in optical fiber is the least. So traditionally, 1550 nanometer is important because the attenuation is the least. 1300 nanometer is important because the dispersion is the least. So you should always remember these two wavelengths, 1550 nanometer and 1300 nanometer. So you call them as the two communication channels or the two optical telecom wavelengths. Optical communication window. So it's commonly referred to as 1300 nanometer and 1550 nanometer. So even though I have specified only one wavelength, it's not exactly one wavelength because you are talking about a window. So there is always a small span of wavelengths at which the dispersion is minimum, and similarly there is always a small span of wavelength range over which the attenuation is minimum. So however, you should always remember these two wavelengths, 1300 nanometer and 1550 nanometer. 1300 important because the dispersion is the least. 1550 is important because the attenuation or the loss is the least. Okay, so if you look at water vapor molecules, the losses due to the presence of water vapor molecules, you will find that the losses due to water vapor molecules attains a maximum. For example, somewhere around 700 nanometer, then around 900 nanometer, again around 1200 nanometer, around 1400 nanometer, and so on. So, so nowadays there are techniques by which you can actually minimize this. You can minimize this water vapor, the losses due to water vapor. Okay, so this is the experimentally measured attenuation spectrum or the absorption spectrum of an optical fiber. So this one, so these two peaks, what you see here, this one is because of water vapor, the presence of water vapor. So we are going to work somewhere around, yeah, somewhere around this wavelength and also somewhere around this wavelength, which is around 1300 nanometer and 1550 nanometer. Okay, any questions so far?
Sir, in the previous slide, what is the overton?
Which one?
Sir, in the previous slide, what
Yeah.
what is the overton? Overton, sir.
Yeah, what is the meaning of overtone? That's simply harmonics. Okay, any other questions?
No, sir.
Okay. So far we studied about what is called as the absorption loss. So absorption loss means, for example, if you have water vapor molecule, this water vapor molecule will absorb a photon, will eat a photon, so that the photon number decreases. So when such a loss happens, you call that loss as absorption loss. So for example, the presence of water vapor, the presence of impurities, all these are responsible for absorption loss. So finally, if the photon is absorbed, then finally at the receiver side, you are going to have a smaller number of photon. So the receiver is going to have a very hard time in deciding whether it has received a 1 or 0. The other class of loss, which is also responsible for the loss of photon number, is what is called as scattering loss. So now we are going to study about what is called as scattering loss. So the scattering loss can be classified into two categories. So before that, so what is scattering? So what do you mean by light scattering? So how do you define light scattering?
Absorption, emission, light.
Which one?
So absorption and emission of light.
Absorption and emission.
Yes, sir. Emission will be in different direction. So it is scattering the light.
Emission are different?
So the absorption and the emission will be in different direction. So it will scatter the light.
Okay, so it's not really absorption. So imagine that you have a photon that is, let's say a photon is traveling through space and it encounters an obstruction. And what happens, so if you have a beam of light and then let's say that there are some dust particles. There are some dust particles. So there is a beam of incoming light and this light can be scattered. Scattered means the direction of propagation can be altered by the presence of these particles. So you call it as scattering. So basically the direction changes. So scattering can be classified into two. So it's called as, it could be either a linear scattering process or it could also be a non-linear scattering process. So linear scattering process means, let's assume that the incoming photon is having a particular wavelength, let's say lambda, or let's say the incoming photon has a particular frequency nu. So after scattering, let's say that the direction changes. The direction changes, however, the frequency remains the same. So if the frequency is unaltered in such a scattering process, you call it as the linear scattering process. It's called as the linear scattering process. So only the direction changes. It's called as a linear scattering process. So a common example of a linear scattering process is what is called as the Rayleigh scattering. It's called as the Rayleigh scattering. In fact, Rayleigh scattering, so if you observe, so if you look at sky, the sky appears to be blue in color. The blueness of the sky is because of the Rayleigh scattering. It so happens that blue is scattered and it's the blue wavelength that appears, it reaches your eyes. And as a result, you see the sky appears to be blue in color. In fact, the sky does not have really a color. It's only because of the scattering events that you see sky as blue. Similarly, in early morning and late evening, the sky appears reddish. So that's also because of Rayleigh scattering. It so happens that the red light gets scattered more, and therefore the red light arrives at your eye early in the morning and late in the evening. So that's why during those two times the sky appears to be reddish in color. So that's also because of Rayleigh scattering. Anyway, Rayleigh scattering is a linear scattering process in which the direction of light changes. However, the frequency remains unaltered. So Rayleigh scattering, so in an optical fiber, Rayleigh scattering is the dominant scattering mechanism that is present. And Rayleigh scattering happens because of the fact that, let's say that inside optical fiber, you have some inhomogeneities. You have some inhomogeneities of random nature whose dimension or the scale is small compared to the wavelength of the light. So you have an optical fiber. So imagine that you have an optical fiber through which you have a photon that is propagating. The photon has a wavelength of lambda. And let's say that the core of this optical fiber has some inhomogeneities. So there are some inhomogeneities inside optical fiber, and the scale of this inhomogeneity is much smaller compared to the wavelength of the light. So in that case, this photon gets scattered, and that scattering is what is called as the Rayleigh scattering. And this Rayleigh scattering is a linear scattering process because the scattered light, the wavelength or the frequency of the scattered light is the same as the frequency of the incident light. So it turns out that in the case of Rayleigh scattering loss, the Rayleigh scattering always is proportional to inverse of the fourth power of the wavelength. So that means if you are using a longer wavelength or a larger wavelength, the losses due to Rayleigh scattering is also going to be small. So therefore, compared to 1300 nanometer, 1550 nanometer, using 1550 nanometer is better because the Rayleigh scattering loss is going to be small. So this is a linear scattering process. The other scattering loss is also called as Mie scattering. MIE. It's called as Mie scattering. So Mie scattering happens when you have an optical fiber and there is a photon that is flowing through that, and there are some inhomogeneities. However, the size of those inhomogeneities is of the order of the wavelength of the light. So in that case, you have a scattering process, and that scattering process is what is called as, so that scattering is called as Mie scattering. So please note that in the case of Rayleigh scattering and Mie scattering, the scattered photon preserves the wavelength. The frequency of the wavelength does not change, only the direction changes. So in such a case, those scattering mechanism is called as a linear scattering mechanism. Now you can also have a nonlinear scattering mechanism or nonlinear scattering process where the frequency changes. So in other words, so if you are talking about an optical fiber, there is always a mode. So there is always a mode, and because of this scattering process, so what happens is the power that is there in one of the mode gets non-linearly transferred to another mode. In other words, the frequency changes. So such kind of scattering process is what is called as a non-linear scattering process, and there are two examples what I can give you. So one is called as, in short, it's called as SBS, which is called as stimulated Brillouin scattering. So SBS is called as stimulated Brillouin Brillouin scattering. The other process, the other scattering, nonlinear scattering process is called as SRS, which is called as stimulated. So stimulated Raman scattering. So in these two scattering process, what happens is the scattered light, the frequency of the scattered light or the wavelength of the scattered light is slightly different from the frequency of the incident light. So you have a photon that is passing through the optical fiber. So there is a photon that is passing through. It finds an inhomogeneity there. There is a scattering. That means the direction changes. So the wavelength or the frequency of this scattered light is different from the wavelength of this incident light. So accordingly, such a scattering event is a nonlinear scattering event. And it can be called as a Brillouin scattering or a Raman scattering depending upon whether the frequency increases or decreases. So anyway, we are not going to too much details of this because that's beyond the scope of this course. But please note that these two scattering process, which are the Brillouin scattering and the Raman scattering, both are nonlinear scattering process, which means that the wavelength of the photon will be changed. And both of them are nonlinear scattering process. So whenever there is a change of frequency or change of wavelength, you call it as a nonlinear scattering process. Whereas Rayleigh scattering and Mie scattering, they are always linear scattering process because their wavelength or the frequency does not change. Okay, any questions? All right. So that's all about the various scattering laws which happens inside the fiber. The other mechanism that is responsible for loss in optical fiber is because of bending. So you call it as bending loss. And bending loss could be micro bending or macro bending depending upon how the fiber is being bent. So micro bending, it usually originates from any non-uniformity when you are manufacturing an optical fiber. Or when you are manufacturing, there could be some kind of pressure that is created inside the cladding. So whenever you are making the, whenever let's say that you make the core of the optical fiber, and then you are trying to coat the cladding. You are trying to form the cladding around the core of the optical fiber. So in this process, let's say that at some point there is some pressure imbalance. So there is some pressure that is exerted during the fabrication of the optical fiber. Let's say that at some point there is a larger pressure that is applied, because of which you can have some micro bending. You can have some bend over there. So that bending is what is called as micro bending. So micro bending usually originates during the manufacturing of optical fiber, because the fiber what you are creating is usually manufactured like a few tens of kilometers or a few hundreds of kilometers. The length of the fiber is extremely large. So it's always very difficult to maintain the uniformity over a very long distance or a very large distance. So because of which you can have some non-uniformity causing some micro bending, and this micro bending would result in the loss of power. So whenever you have some micro bending, some kind of micro bending there, because of this micro bending, total internal reflection will not be always satisfied here. So because of which the optical fiber, so in this part some of the photons can actually leak out, because total internal reflection, the condition of total internal reflection may not be obeyed at this point. So you call it as micro bending, and because of this micro bending you can have some losses. The loss means you are losing photons, the receiver loses power. And macro bending happens when you take a straight optical fiber and then you bend it. For example, here is a straight optical fiber, and let's say that I'm bending here. So when I'm bending there, you would see that some of the power. So the plot what you see here is actually the plot of electric field. So you would see that there is a significant amount of leakage here. So you would see that so the optical the power that is being confined inside the optical fiber starts leaking out because of macro bending. So in whatever be the case, whether it's micro bending or macro bending, this is what happens. That so if you have a straight fiber with no bending, you would see that the rays would always undergo total internal reflection. So whenever you have this kind of bending there, you would see that total internal reflection the ray need not always undergo total internal reflection, which means that if you are plotting the profile, if you are plotting the mode profile, you would see that inside cladding, you would see that there is a significant amount of optical power. So you call this wave as the escaping wave. The wave escapes from the fiber because of bend. So whenever you are laying optical fiber, it's always better to make sure that the fiber is always bent in the form of straight line. Well, you cannot always put it exactly in straight line, but you can always have some bend. But the bending would be always, you can have some significant amount of tolerance. That means you cannot perfectly make it straight line, but some small bending is always possible. But if the bending radius exceeds certain critical value, then you can have significant amount of leakage. So for example, if I take an optical fiber and if I am bending like this, so this would cause a 1 dB loss, this would cause a 4 dB loss, and if I am still bending it more, this will actually break the fiber. So if it breaks the fiber, then it becomes useless. So I should not bend the optical fiber like this. So I should not bend the optical fiber like this. So it's always better to maintain to have optical fiber to be laid like this, straight. Whereas if I am putting like this is still okay. There is some bending, but this is still okay. Whereas if I take an optical fiber and then if I am rolling it like this, then this is going to cause significant amount of loss. And if I make this more and more, if the bending is more and more critical, then it can actually break an optical fiber. You can break the optical fiber, then it becomes useless. So these are some of the points what you need to consider whenever you are laying an optical fiber. So losses has to be always minimized, for which it's always preferential to have to keep the optical fiber in a straight line. However, not exactly a straight line. Some kind of bending is always allowed, but not too much. All right, any questions? Okay, so bending in an optical fiber is not always a disadvantage. For example, you can exploit the losses that happens in bending for detecting something. For example, let's say that you have a straight optical fiber, there is a light source, and let's say that I'm not applying any mechanical pressure. So whatever light I'm launching would be appearing at this point. So I can have a photodiode and this can detect what is the amount of light that is coming. Now let's say that I'm applying some pressure. So once I increase the pressure, you would see that because of larger amount of bending, the output power is going to be reduced. So this power what I am receiving is proportional to the pressure what I have applied here. So I can actually make a pressure sensor here. Pressure sensor. So I can always I can always make a sensor which can detect the amount of pressure what is applied. So it could be pressure, it could be strain, it could be many things. So you can use this, you can take advantage of bending laws in optical fibers to decide what is the pressure that is being applied. So this is one such example where even though the bending loss is bad, you can take it for your advantage.
Sir?
Yeah.
So we need to make sure that it regains its original shape also, when pressure is not applied.
When pressure is not applied, yeah, of course, yeah. So when the pressure is not applied, you'll have to ensure that the fiber retains the original shape. Yeah, usually optical fibers usually retains the optical shape. Usually regains the original shape, unless you apply enormous amount of pressure, and then if you apply such a large pressure, then it's going to break it. But nominal pressure, whatever you are applying an optical fiber, it's going to the optical fiber is going to regain its original shape.
Okay.
All right. So when we make optical fibers, usually fibers are made. They are very thin strands of optical fiber, very thin strands of silica fiber. So by the way, if you compare the dimension, if you compare the size of if you compare the core size of an optical fiber and the size of your human hair, so what is the typical size? What is the typical diameter of a human hair?
Micrometer.
Yeah, but how much micrometer? So the typical diameter of human hair is of the order of 100 microns. If you take a single mode optical fiber, the core diameter is going to be only 6 microns. Let's say 6 to 10 microns. So just for comparison. So this is the typical comparison. A single mode optical fiber usually has a core diameter of the range 6 to 10 micrometer, which is in fact 10 times smaller than the average diameter of human hair. So they are so narrow. They are so narrow, they are so flimsy, and that's why you need to have, and core is the one which carries the optical power. So you'll have to ensure that the core is well protected. It's well protected from external light, external photons, and also it should be mechanically protected. That's why you take a core, then you take a cladding, then you put another protective cover, then you put another jacket. All these multiple layers of coating is provided because the core is very thin and it needs a lot of protection layers. All this cladding and protective jackets and so on. So these two, the core and cladding is usually made out of silica. This one and this one. So core and cladding is made out of silica. The other ones, the other protective layers could be made of polymers or rubber. So those are the protective covers. However, the one which carry the power, the one which carry the information signal is actually the core, which is very narrow in diameter. So you can make optical fibers which are very long. Let's say you can easily make optical fibers as long as 200 kilometer. But unfortunately, laying 200 kilometer optical fiber inside ground is going to be difficult. In other words, deploying them is very difficult. So what you do? So what you do is you take instead of putting a very long optical fiber, what you do is you make small optical fibers, let's say which are like let's say 50 kilometer long, or let's say 40 kilometer long, and then you join them. So you join optical fibers. So when you physically join two optical fibers, you call it as fiber splicing. Fiber splicing. Splicing is when you mechanically join two optical fibers. Fiber splices or fiber splicing. The process is called as fiber splicing, and if you join two optical fibers, you call it as fiber splices, or you say it as spliced fibers. Spliced fibers. So spliced fibers is very similar to the electrical joints, the soldered joint. So let's say that you take two wires and you join them, or you solder them. So that is one way. So that is one way in which you can connect to electrical wires or copper wires. So when you join to electrical wires by soldering, so at that joint where you have soldered them, there is always going to be a loss. There is always what you call as ohmic loss. So ohmic loss means you are going to have some I square R loss. That means there is going to be some increased resistance over there, and as a result you are going to have some drop. Some voltage is going to be dropped over there. That's what happens. If you have large number of soldered joints, then at every soldered joints you are going to have some ohmic loss, I square R loss. So whatever voltage what you are applying, so some of the voltage get dropped over there. The same thing happens in the case of optical fibers also. So instead of I square R loss, you have a different kind of loss which is called as the Fresnel loss. Which is called as the Fresnel loss, which is very similar to the ohmic loss. So in the case of ohmic loss, you use some voltage. In the case of Fresnel loss, what happens is you lose some photons. Now you might have seen some electrical joints which can be removed, which is not a permanent joint, which can be removed. So you can also have similar kind of temporary joints in optical in the case of optical fibers as well. So when you join two optical fibers, one very important factor what you need to account for is what is called as the alignment of optical fiber. So you call it as the fiber alignment. So fibers have to be well aligned. In the case of electrical wires, so when you join two electrical wires, you are not very critical, you are not very cautious about the way in which they are aligned. Though you would use your naked eye to make sure that they are well aligned, but you don't have to use a microscope and then align it. However, in the case of optical fibers, because their diameters is extremely small, you will have to ensure that the two optical fibers that you are going to connect, they are well aligned because of their small radius. So whenever you are joining two optical fibers, so let's say that I have one optical fiber, so this is optical fiber 1, and I'm having another optical fiber, let's say this is optical fiber 2. So when I'm joining them, so this is one end of the optical fiber, this is the other end of the optical fiber. So this optical fiber is going to have a core. So this is the core, this is the clad, and similarly for this optical fiber also, this is the core, this is the clad. So let's say that I am joining two optical fibers. I'm trying to connect two optical fibers. So they have core and cladding. Now let's assume that if these two optical fibers, if the refractive index of the core of these two optical fibers is exactly the same, then it's wonderful. That means if the core refractive index of the first optical fiber is exactly the same as the core refractive index of the second optical fiber, then it's wonderful. That's the perfect situation. So when you join them, almost no losses. But in practice, what happens is when you make optical fibers or when you are joining two optical fibers, there is a very good chance that the refractive index of the core of the first optical fiber is slightly different from the refractive index of the core of the core refractive index of the second optical fiber. That means there is a refractive index mismatch between these two optical fibers. So there is a refractive index mismatch between these two optical fibers. So when the power from the optical fiber 1 is trying to enter the second optical fiber, it sees a refractive index difference, because of which there is a reflection, and that reflection is what is called as the Fresnel reflection. It's called as Fresnel reflection. It's called as the Fresnel reflection. And that reflection coefficient is given by the Fresnel reflection coefficient R, which is given by n1 minus n divided by n1 plus n the whole square, where n1 is the refractive index of the core of the first optical fiber, and n is the refractive index of the core of the second optical fiber. So n1 minus n divided by n1 plus n the whole square is what is called as the Fresnel reflection coefficient. And the Fresnel reflection loss is given by minus 10 log. So minus 10 log to the base 10, 1 minus r. So if the refractive index mismatch is large, then the Fresnel reflection coefficient is large, and accordingly, the loss also is going to be large. So when you are joining two optical fibers, or when you are splicing two optical fibers, you will have to ensure that the refractive index mismatch between the two optical fiber is as small as possible, so that the Fresnel loss can be minimized. So when you join two optical fibers, you can also have a situation where you place two optical fibers, and then you fill in with, so between these two gaps, you fill in with what is called as an index matching liquid. Index matching liquid means it's a refractive index matching liquid. So you are filling it with a liquid whose refractive index is somewhere close to these two refractive indices, so that the Fresnel loss can be minimized. So you will have to take care of alignment, and also you will have to ensure that the refractive index mismatch between these two optical fiber is minimum. So we'll see more details about the fiber alignment. So let's say that I'm trying to join two optical fibers, or I'm trying to align two optical fibers. So axially they are well aligned, but there is some mismatch over there. So if there is a gap like this, so if the axis of these two optical fibers are exactly aligned, but however there is a difference, there is a slight misalignment in their facets, then you call it as the longitudinal misalignment. Whereas in these two cases, their faces are joined together, but there is a misalignment in their axis. You call it as the lateral misalignment. There's a lateral misalignment. Whereas in these two cases, their axis is not aligned properly. So you call it as the axial misalignment. So you can have longitudinal misalignment loss, you can have lateral misalignment loss, you can also have axial misalignment loss. So you can also have losses when you are joining two optical fibers. Let's say that the diameter, the core and the cladding diameters are different. So that is shown here. Let's say that you are joining two optical fibers. So one is having a larger diameter, the other one is having a smaller diameter. So if the light is being launched from left to right, then you are going to have significant loss, which is given by this expression, where A1 and A2 is the diameter, is the radius of these two optical fibers. If I am trying to launch from right to left, then you are not going to see a significant loss, because it's the signal is trying to enter a optical fiber having a larger core. So in that case, the losses is going to be 0. Similarly, when you are trying to join two optical fibers, you will have to ensure that the numerical aperture of these two optical fibers matches. So if I am trying to launch from left to right, let's say this is the first optical fiber, this is the second optical fiber. So let's assume that the second optical fiber has a smaller numerical aperture. So remember the definition of numerical aperture, it defines the ability of an optical fiber to collect the light. So this one has a larger numerical aperture, this one has a smaller numerical aperture, because of which you will lose some of the light. If the second optical fiber has a larger numerical aperture compared to the first one, then you are not going to have any loss. Similarly, the refractive index profile of the two optical fibers is also important. So you'll have to ensure that the refractive index profiles of these two optical fibers also matches. So if you plot the losses, if you plot the insertion loss, so by the way, what is insertion loss? What do you mean by insertion loss? So let's assume that you have a transmitter, I have a receiver, and there is a straight optical fiber, a single optical fiber. Now consider the second scenario where I have a transmitter, I have a receiver, and let's say that I'm having two optical fibers that are connected here. So at this point, I have connected an optical fiber. So that means in this optical communication link, I have actually inserted a connector. The only difference between this one and this one is that in both the cases, the transmitters and the receivers are connected by optical fiber, but in this case, the connection is through a connector. I have joined these two optical fibers. That means I have inserted a connector. So because of this connector, because I have inserted a connector, is going to add an additional loss. So that loss is what is called as insertion loss. You can also call it as a connector loss, but generally you can call it as insertion loss. So this insertion loss becomes serious if, so here I have plotted the losses because of the insertion loss because of longitudinal misalignment and because of lateral misalignment. So lateral misalignment is this one. This is lateral misalignment. So compared to longitudinal misalignment, lateral misalignment is serious because you're going to lose significant amount of power. So you'll have to ensure that the numerical aperture is same. You'll have to ensure that the core diameter is also the same. You'll also have to ensure that the refractive index profiles are the same. Okay, I'll stop here. We'll continue the remaining things in the next class. So any questions so far? If no questions, we'll stop here. Okay, we'll continue the next class. Okay, thank you all.